Hi, this is Sunita, Assistant Professor ECA Department, Siddharth Academy of Higher Education, deemed to be university. So, in this lecture, we will see the need for biasing. What is biasing? Need for biasing, stabilization factors, and fixed biasing technique. We will see the fixed biasing technique in this lecture. What is biasing? The DC voltage is applied to a transistor in order to turn it on so that it can amplify the AC signal. So the main application of the transistor is acts as an amplifier. So to act as an amplifier, the output signal should be the increased strength levels of the input signal without distortion. We will get the amplified signal, proper signal without distortion. To get the undistorted signal, the DC voltages should be properly applied to a transistor for the AC input signal amplification. How a transistor can be biased? A transistor is biased either with the help of the battery or associating a circuit with the transistor. What is Q point? The DC input establishes an operating or quiescent point to get the distortionless output, to get the faithful output. So the point where the output is distortionless, the output is faithful, that point is called the operating point or quiescent point or Q point. Normally the point is voltage comma current, VCE comma IC. We will see that a Q point in next slides. See, so we know that transistor is operated in the three regions. Uh, both the junction, active region if the input junction is forward bias, output junction is reverse bias. Cutoff region, both the junctions are reverse bias. Saturation region, both the junctions are forward bias. We know that in active region, transistor acts as an amplifier. So the Q point should be in the active region. The operating point should be in the active region. In the active region, where exactly? See, this is the output characteristics. The cutoff region, this is saturation region. This entire the portion we will call the active region. This entire the portion is the active region. So in the active region, where the Q point must be, should be placed, this level, this level, this level, this level. What will happen if Q point is nearer to the saturation level? If the DC voltages are fixed, if the DC voltages are fixed nearer to the saturation level, the upper peaks of the output signal, get clipped. The upper peaks of the output, the amplified signal, the positive peaks will be clipped off. What will happen if the operating point is nearer to the cutoff region? If the operating point is nearer to the cutoff region, the output signal negative peaks are clipped. The amplified signal negative peaks are clipped in the if the operating point is nearer to the saturation cutoff region. Then where we need to fix the operating point means middle of the active region. This is the active region. In the middle of the active region, we need to uh, stabilize the operating point. We need to choose the operating point middle of the active region to get the distortionless faithful output. So through the proper biasing, the desired quiescent point or operating point of the transistor amplifier in the active region, the amplitude of the signal to be handled by the amplifier and the distortion level of the signal, the load to which the amplifier is to work for the corresponding supply voltage. So to get the faithful output, distortionless output, we need to fix the operating point. That operating point shifts, operating point may change. If the operating point change means the output will get distorted. So on what factors operating point will depend means, since the operating point transistor parameters like beta, if beta is varies from transistor to transistor, and temperature, and IC naught and VBE. If the temperature changes, IC naught changes and VBE changes. So the operating point depends on the beta value, IC naught, that means if temperature changes, IC naught changes and VBE. So we need to see that how much the operating point is stable with respect to the changes of beta, with respect to changes of IC naught, with respect to changes of the VBE. So those factors are called the stabilization factors. How much the operating point change with respect to the beta, with respect to the IC naught, with respect to the VBE. So our aim is transistor acts as an amplifier, we need to get the distortionless faithful output. To get distortionless faithful output, we should fix the operating point at the middle of the active region. So what are the factors change the operating point? If you know that, we need to fix that point, that changes should be the fixing. So beta, IC naught and VBE. Now for the biasing stability, for the knowing the stability, how much stable this circuit, we need to find out the stability factors. So this is the DC operating point common emitter configuration. Output is VCE, input is IC. So this is the uh, load line. So see here, this point 1, this point 1. So this total Q1, Q2, Q3 are the all these the active region. Q3 nearer to the saturation, Q1 nearer to the cutoff. So Q2 middle of the active region. If you fix the operating point at the Q2, we will get the distortionless faithful output. So DC load line, CCE configuration, VCC applying resistance RB RC. For AC, make AC is equal to 0. We need to use the by DC supplies. We need to fix the operating point. So make AC 0 without applying input voltage. So VCC. Here the output, see the KVL for the output. VCC is equal to voltage drop here ICRC. The voltage between emitter and collector is VCE. So the total voltage VCC is equal to ICRC plus VCE, output loop equation. If you want to put input loop, VCC is equal to the current drop, voltage drop here is RB plus IB, RB into IB. VCC is equal to IB RB plus, here the voltage drop is cut in voltage VBE. VCC is equal to input loop, KVL to the input loop, VCC is equal to IBRB plus VBE. KVL to the output loop, VCC is equal to ICRC plus VCE. See. So a collector circuit, VCC equal to ICRC plus VCE. See, from this, IC is equal to VCC minus VCE by RC. So we know that basic equation. To get the point on x-axis, put y is equal to 0, IC is equal to 0, x-axis point VCE is equal to VCC, at IC is equal to 0. To get point on y-axis, put x-axis as 0, put VCE is equal to 0. In this equation, VCE is equal to 0, IC is equal to VCC by RC. So, operating point here is VCE comma IC. X-axis VCE, y-axis point IC. The Q point is VCE comma IC. How we will get means, put y-axis 0 to get the x-axis point, put x-axis 0 to get the y-axis point. So base circuit, VCC is equal to IBRB plus VBE, input KVL. So from this IB is equal to VCC minus VBE by RB. VB is for silicon cut-in voltage 0.7. If you know the VCC and RB, we will find out the IB. So stability factors. Stability factors indicate how the circuit is stable with respect to a particular varying the particular parameters. The stability factor is a measure of the stability provided by the biasing circuit. The stability factor indicates the degree of change in operating point due to variation in the temperature. So stability factor S is changing the operating point due to the variation of the temperature. Here the stability factor is change. Uh, we to stable the circuit, the operating point should not change. But here the stability factor indicates the how much change. So definitely the circuit must have the less stability factor. So here we have the three stability factors because of three parameters VB, IC naught, beta and BB are the parameters. So S, stability factor S is the rate of change of collector current with respect to the IC naught, while beta or BB are constant. Remaining two parameters are constant. How much collector current changes by changing the reverse saturation current IC naught. The second stability factor S dash. S dash is the rate of change of IC with respect to the change of the VBE. How much collector current change by changing the VBE while other two parameters are kept constant, IC naught and beta. S double dash. How the change of collector current with respect to the change of the beta, that means by replacing the one transistor to the other transistor, while remaining two parameters VB and IC naught are constant. So these are the stability factors to fix the stability of the circuit. For the circuit, which one has the stability factor less? That means the change. Stability factor means the change. How much change of IC? IC is nothing but one of the operating point voltages. VCE comma IC is the quiescent point. How the IC is changes? IC should not change because if IC changes, Q point changes, we will get the distorted output. Whatever the parameters is changes, if IC is constant, the Q point will be constant, we will get the faithful output. See, we will derive the expression for the stability factor S, dou IC by dou IC naught when VB or beta is kept constant. We know that equation IC, collector current is equal to majority current plus minority current, IC plus IC naught. IC naught means minority current, reverse saturation current. So IC naught equal to ICB. From this equation we will get IC is equal to beta into IB plus 1 plus beta into IC naught. Beta is the CE current gain. So we need to get the S. What is the formula for this? Dou IC by dou IC naught. So divide this equation with respect to the IC. So 1, we will get this. So we need to get the dou IC naught, dou IC by dou IC naught. So dou IC naught, make this dou IC naught by dou IC is equal to this one. So substitute S is equal dou IC by reverse 1 plus beta by 1 minus beta into dou IB by dou IC. If you want to find the stability factor, if you want to find the stability factor of the particular circuit, we need to find out the S. So how we can find out the S? By finding the dou IB by dou IC. Find out the base current IB, differentiate this with respect to the IC or IC with respect to the IBE. So substitute here, we will get the S value. C. So thermal stability IC dou IC by dou IC naught. This is the formula. So now we will see the fixed bias circuit. We will see the fixed bias circuit. So this is the fixed bias circuit, common emitter configuration. Input is base, we are collecting output across the collector. So this is the AC input signal. For the proper biasing, we need VCC. We applied VCC DC voltage to fix the operating point. We applied the DC voltage. So the in output loop is VCC is equal to ICRC plus VCE. VCC is equal to ICRC plus VCE. For the input loop, VCC is equal to IBRB plus VBE. VCC is equal to, here the V applied to the base circuit, applied KVL to the base circuit because we need to find out the stability factor S. S is 1 plus beta by 1 minus beta into IB by dou IC. By finding the IB value and differentiate this with respect to the IC, this value we can substitute in the formula. So we need to find out the IB. So for that, do the KVL at the emitter base circuit. VCC is equal to voltage drop here IB plus IB into RB plus VBE, cut in voltage here VBE. From this, IB is equal to VCC minus VBE by RB. So VBE take as a less, where compared to the VCC, VBE is very less. VCC nearly we will give the 12 volts, like 15 volts, but VBE is a 0.7 or 0.3. So we can neglect VBE when compared to the VCC is the high voltage. So IB is approximately equal to IB is equal to VCC by RB. So to find out the VCE, the operating point is IC comma VCE. To find out the VCE, so see output loop equation here. VCC is equal to ICRC plus VCE. VCC is equal to ICRC plus VCE. So VCE is equal to VCC plus ICRC. From this equation, we will get the IC. So what are the stability factor? S formula 1 plus beta by 1 minus beta into dou IB by dou IC. So we have IC value, IC equal to VCC minus VCE by RC. Differentiate this with respect to the IB. There is no IB term, IB constant, so 0. This term is 0 means 0. S is equal to 1 plus beta. S is equal to 1 plus beta. That means the stability factor is 1 plus beta. So beta, what is the beta? Beta is the current gain. Beta is varies with respect to the transistor to transistor. That means the stability factor is depends upon the beta value. If the transistor vary, beta value varies, the operating point vary. Operating point varying means we will get the distorted output. So that also S value is very more because the beta is the current gain in terms of 299, 100 like this for CE amplifier, CE configuration. CE configuration both current gain and voltage gains are high. So beta is like 50, 51 like this. So S value is more. What reveals the S value? How much stable? The rate of change of collector current with respect to IC naught. So if the temperature changes, IC naught changes. IC naught changes means IC changes. So the rate of change indicates the S value. The rate of change should be less. S value should be less for the stable circuit. So for the fixed bias, S value is very more. Next, we will find out the S dash. S dash means the rate of change of IC with respect to the VBE, while beta and IC naught are kept constant. We know the equation IC is equal to beta into IB plus 1 plus beta into IC naught. So IC, from this equation we find out the substitute IB value here. From this substitute IB value here, we will get here. Differentiate with respect to IC with respect to VBE. So S dash we will get minus beta by RB. Again S dash also depends upon the beta value. If you change the transistor, S dash value changes. If the stability factor changes, that means the rate of change is more. The rate of change is more means the circuit is less stable. So we will see the merits and demerits. Merits means simple circuit with less number of components. Simple circuits, less number of components. This is the merits. Demerits means the collector current does not remain constant with variations of the temperature or power supply. Therefore, the operating point is unstable. With respect to the temperature. Temperature changes, IC naught changes. That means the S value is more. When the transistor is replaced with another one, there is a change, considerable change in the beta can expected. So this also change the shifting of the operating point. So finally, the fixed bias is simple circuit with less number of components and easy to analysis, but does not used for the to fix the operating point. If the temperature changes, operating point changes, we'll get the distorted output. If you replace the transistor with the another transistor, we will get the distorted output. So fixed bias circuit, even though it is easy, number of components are less, very simple circuit, we are not going to use this fixed bias circuit in the practical circuit because of the stability factors, high stability factors. The circuit is less stable. Stability factors, I means the circuit is less stable. Fixed bias circuit is less stable with respect to changes of the temperature and beta value. In next class, in next lecture, we will see the collector to base bias and the self bias circuits. Thank you.